So we're asked to determine the force in members CD, CF, and FG, and state if these members are in tension or compression. So since we're only asked for 3 specific members, and they're all kind of located near each other, so CD, CF, and FG, the most appropriate solution method is probably going to be method of sections. This is because we can just take one cut through this part of the structure and be able to solve directly for all 3 of those forces that we're interested in. If we were to apply method of joints instead, we'd have to pretty much work our way across the truss from like left to right. So that means, or right to left I should say, so that means we're going to have to solve for a lot more forces within the truss. So doing method of sections just, I guess, cuts down the amount of time and the amount of work that you need to do. So the first thing I'm going to do is draw the free body diagram of this overall structure and take a look at what I need to do when I cut it. So looks something like this. So we have some externally applied forces. This one. And we're going to need to replace each of our supports with the reactions. So at A here we have a pin joint, so that means it's going to react with a vertical and horizontal component. I'll call them AY and AX. And here we have a roller joint, so it's only going to have a vertical component. It's vertical because it's perpendicular to the surface. So the surface is horizontal, that means we get a vertical reaction. So I'll call this one EY. So we're only really interested in the forces in these 3 members. So we said CD, CF, and FG, these 3 here. So we can perform a cut through each of those 3 members and completely split this truss into 2 pieces. What that's going to mean is that we only need to take either the left-hand side or the right-hand side to analyze the forces internally within these 3 members. And in order to do that, we're going to need either the reaction here or we're going to need the 2 here, depending on whether we take the left-hand side or the right-hand side. So I think I'm going to try and take the right-hand side just because we've only got one thing we need to solve for then. And we can get this EY force by just looking at the whole free body diagram. And if we sum our moments about point A here, we should be able to work out what EY is. Alright, so AX, AY and the 2 kilonewtons act through point A, so they're not going to create a moment, so we don't put them in the equation. Next we have the 4 kilonewtons, and this is going to be acting at a distance here of 5 meters, and it's going to try and pull it anti-clockwise, so it's negative. The next force is also 4 kilonewtons, but it's acting at a distance of 10. It's also going to try and pull this in clockwise. We've then got this one of 5 kilonewtons acting at 15 meters. It's also going to try pull it clockwise. We've got the 3 kilonewtons acting at 20 meters. It's also going to try and pull it clockwise. And finally we have EY, which is going to try and pull it the opposite direction, which is anti-clockwise, and it's also at 20 meters away. So the only unknown is EY, and if we solve for this, it comes to be 9.75. kilonewtons, since all our forces are in kilonewtons. So I can mark that in here. Alright, so now I'm going to take my cut part of the truss. Like I said, I'm going to take the right hand side, so that's why I'm not solving for these other ones. So redrawing just this part. And I'm going to draw each of these forces in tension, tension for each of these unknowns, and we'll give them some labels. So this one was CD, this one here is CF, and this one is FG. So we also have some externally applied forces that we need to carry across. So we've got this 5 kilonewtons, we've got the 3, and we've got the 9.75 from the reaction. Now we're also going to need some angles for these forces in here, and we can work out what angle they are with respect to the horizontal relatively easily. So if I take out the, I guess, triangle that sits in here, this one. So we know that this length through here, the horizontal part, is 5 meters. And we know that this bit, the vertical part I guess, is 3 meters. So that's this bit. And we know that this bottom part here is going to be 2. So I'm going to work out these two angles. I'll call them theta 1 and theta 2. We know these are right angled triangles. So it's going to be tan inverse of the opposite over the adjacent. So that's 3 on 5 for the first one. And this comes to be 30.96 degrees. For the second one, it's going to be tan inverse of 2 on 5. And this comes out to be 21.80 degrees. So these are the angles that I can apply each of the forces at in my free body diagram down here. So this one is 30.96. This one was 21.8. Alright, so I now have a free body diagram that has 3 unknowns, and I have my 3 simultaneous equations that I can apply. So I think the best choice is to start with doing sum of moments about this point here, which is F, because if we sum about that point, both of our these 2 unknowns act through the point, so they're not going to appear in the equation, and the only unknown should be FCD, and we can work it out quite easily. So that's my approach here. Alright, so FCD needs to be multiplied by the distance in here, and we can get that off the diagram. It was 3 meters. Let me show you. So it's basically the length of this member. If we scroll back up, this member in here is 3 meters long. And this is going to try and pull us in an anti-clockwise direction about our point of interest F. So it's going to go in as positive. The next one I'll consider is this 5 kilonewtons, and in fact its line of action is going to go directly through F, so it's not going to create a moment, so it's not going to enter into the equation. We'll then consider the 3 kilonewtons, so it's got a size of 3, and it's going to be at a distance of the horizontal part in here, which was 5 meters from the diagram. And this is going to try and pull clockwise about point F, so it's going to be negative. And then we have the 9.75. It's also going to be at a distance of 5 meters, but it's going to be the opposite direction, so it's positive. And we know this all has to be equal to 0. So we can solve for FCD, and it actually comes out to be a negative number of 11.2 kilonewtons. So since it's come out negative, that means we actually had the wrong direction on the diagram. So FCD is actually 11.2, but going back the other way to the right. So let's fix that up. So it's actually back this way. Alrighty, so now that we've got that one, we just need to solve for these other 2. We can do that by doing sum of forces in the x direction and sum of forces in the y direction. Now unfortunately both of these have x and y components, so it's going to have to be solved simultaneously. Alright, so let's start with sum of forces in the x direction. Has to be 0. So we're going to have the positive component from FCD, and we just worked that out to be 11.2. These are all only have y components, so they're not going to be in the equation. And then we're going to have both of these going in the negative direction. So negative FCF, it's going to be the cos component. And negative FFG, again, it's going to be the cos component. Alright, so now we just need to apply sum of forces in the y direction, and it will give us a second equation with the same 2 unknowns, so we'll be able to solve them simultaneously. So we have 3 external forces only in the y direction, so we've got negative 5, negative 3, and positive 9.75. We have a component of FCF, it's going up, so it's going to be positive. It's going to be the sine side of the triangle. And FFG is going downwards, so it's going to be negative. Again, the sine side of the triangle. Alrighty, so now we just need to simplify this down and then rearrange it so that we can substitute them into each other. So putting these ones together, it becomes 7.75, and I'm just going to leave these as they are for now. Now I'm going to need to rearrange for one of these unknowns. I'm going to try and go for FCF, but it doesn't really matter which one. So I'm going to move everything else to the other side of the equation. I'm going to get FFG sine 21.8 and minus 7.75. And I need to divide by sine 30.96 to get FCF on its own. And this becomes 0.722 FFG minus 3.401. Alright, so let's label these equations. So this is equation 1 and this is equation 2. And I'm going to substitute equation 2 into equation 1. So we get 11.2 minus FCF, so this is going to get replaced. It's still multiplied by this on the end. Alright, we still have minus FFG cos 21.8 as well. So now we've made it so we only have the one unknown in the equation, so it's just a matter of solving for it. If I go ahead and expand out these brackets, I end up with negative 0.619 FG, and this is going to become a double negative, so it's positive, and this times this comes out to be 2.917. So if I put these two constants together, 11.2 and 2.917, I end up with 14.167. And I'm going to swing this to the other side and this to the other side, the two terms with FFG. And when I put them together, I get 1.547. So I can get the force on its own. It becomes 9. Got to round it, 2 kilonewtons. Alright, so this has come out positive, which tells me I had the correct direction on the diagram. So if I just go back over here, we had drawn FFG here to be pulling away from the joint F, so that means that it was going to be a tension member, and it was correct, so we can write that in. So now we just need to figure out what FCF is, and we have our equation 2, which we can use for that. FCF is equal to 0.722 multiplied by the number we just worked out, 9.2, minus that extra little bit. And this one comes out to be, I'm going to round it as well, about 3.2 kilonewtons. Again, it's come out positive, which tells me I had the direction correct on the diagram. So if we scroll back up, we can see that FCF was drawn to be pulling away from the joint, which means it was a tension member, and this was correct. So we can jot that in as well. Alright, so that's the answer to all of that question. See you in the other videos.